This lesson 3.4, we'll be looking at systems of nonlinear equations. That is, at least one of the equations is nonlinear. In other words, you could have a first degree equation which could represent a line, possibly a plane, and the other one could be second degree that may represent a circle or a parabola or an ellipse and so forth. So when you solve these types of systems, again, you're looking for the points where the two graphs intersect, assuming you have two equations. So let's look at some diagrams of what you might have. You could have a circle here, which is second degree, and a linear equation which represents a line. So maybe the circle and the line do not intersect. So in that case, there's going to be no solution set for that particular system. Or in the next one, you could have the circle and the line intersecting at 2 points. You'd have two solution pairs. Or you could have, say, maybe two ellipses. In this case, the ellipses intersect at 4 points, so you'd have 4 solutions. So let's look at some examples of how to solve these types of problems. Solve each system. Okay, so I have y equal to 6 square root of x. So notice if I square both sides of that first equation, I get y squared is equal to 36x. So actually the first equation represents a parabola. And because it has a positive square root, it's the top half of a parabola that opens to the right. The thing about these types of problems, since we're solving these algebraically, you don't really have to know what the graph represents. You simply go ahead and solve by elimination, or a combination of elimination and substitution, which is what we did in the first lesson for this particular chapter. So we have y equal to 6 radical x, y equal to 7 minus x. So what we could do is use a substitution and say, okay, y is equal to 6 radical x. So I could replace the y in the second equation by 6 radical x. Or I could say y equal to 7 minus x. So in the first equation, I could replace the y by 7 minus x. Either way, I get the same equation right here that I have. Or I could solve by elimination, multiply the first equation by -1, and then add the y's cancel out, and if I rearrange the terms, I get the same equation. Okay, so there's various ways to do it, but basically you're using elimination, substitution, or a combination of both of these. So I wind up with this equation right here. So normally if I have a radical equation, the procedure is that I square both sides to eliminate the radical. I isolate the radical and then square both sides. Okay, so if I square the left side, I get 36. The radical cancels, I get 36x. And then 7 minus x quantity squared, that's 7 minus x times 7 minus x. If you multiply that out, you get 49 minus 14x plus x squared. Okay, then you bring the 36 over to the right side, combine it with a minus 14x, minus 36x minus 14x gives me minus 50x. I get this trinomial on the right side. And then I just rearranged it, x squared minus 50x plus 49, and then I factored it out into x minus 49 and x minus 1. So that tells me that x can be 49 or x could be 1. Okay. So these are the possible values of x. So then we want to find the values of y that go with these particular values of x. So we go back and substitute into the first equation or the second equation. So let's do it this way. Let's replace the x by 1 in the first equation. So I replace the x by 1 in the first equation. I get 6. Okay. So this tells me that when x is 1, square root of 1 is 1 times 6, y is 6. Okay. Notice if I put the 1 in the second equation, 7 minus 1 is 6. So when x is equal to 1, I get 6. So that particular solution, that ordered pair, satisfies both equations. Now let's do this. Let's put the 49 where the x is in the first equation. So put a 49 right here. Square root of 49 is 7. 7 times 6 is 42. So that tells me with x is 49, the y value is 42. But notice if I put the 49 in the second equation, okay, in the second equation, I put 49 where the x is. 7 minus 49 gives me a negative 42. So this is not going to work for both of them. Okay. So the 49 here, x equal 49, is not going to work. And that's what's going to happen anytime you square both sides of an equation. Okay. When you square both sides of an equation, there's always a possibility of introducing what is called extraneous roots. So they might work for one of the equations, but not for the other. So to be a solution of the system, it has to satisfy both. Okay, so we have to discard the x equal 49 as a possibility, so the only solution is 1, 6. And you can easily check and see that it's going to work for both, but the others are not. Okay. So in this case, I can write my solution as an ordered pair, or I can write it as a solution set this way. X equal to 1, y is equal to 6. That's my solution. Okay, in the second one, I have y is equal to 2x minus 5. That represents a line. And the second one is x squared plus y squared is equal to 10. That's a circle. Okay, the second represents a circle of radius square root of 10. But again, it's not necessary for you to know what the graph represents because we're going to solve it algebraically. So again, since the first equation is solved for y, and it tells me that y is equal to 2x minus 5, I plug in that value or that expression in for the y in the second. So notice up here in the steps where I have the y in the second equation, I put 2x minus 5, and then I squared both sides. I'm sorry, and then I squared that because it's y squared. So 2x minus 5 squared gives me this 4x squared minus 20x plus 25. And then I collect my terms. You can see it's going to come out to a quadratic equation. And that's the object in solving systems. You want to use substitution or elimination so that we can go from two variables to one variable and solve for that particular variable and then plug into the other equations to find the value of the y or the x depending on which one you solve first. So in this one here, once I've squared the binomial here, I bring the 10 over. 10 subtracted from 25 is 15, so I get 5x squared minus 25x plus 15 is equal to 0. Simplify this a little bit by dividing through by 5. Since 5 divides all the terms, 5 into 5, 5 into minus 20, 5 into 15, I get x squared minus 4x plus 3 is equal to 0. Okay. And then I factor this out. Factors into x minus 3, x minus 1. So that tells me then that possible solutions then are going to occur at x equal 3, x equal 1. So we want the y's that correspond to these. So again, I always like to pick the simplest equation. So the first one is a line. It's already solved for y, so I put a 3 where the x is. So if x is equal to 3, okay, so put a 3 right here where the x is. 3 times 2 is 6. 6 minus 5 is 1. So one solution is the ordered pair 3, 1. When x is 3, y is 1. So you can easily check it. Obviously it works in the first one because I got those values from that one. But so let's make sure it works in the second one. 3 squared is 9. 1 squared is 1. 9 and 1 equals 10. So it does satisfy that one. Okay. Now let's try the next value. X is equal to 1. Okay, into the first one, so put a 1 there. 2 times 1 is 1, minus 5 is negative 3. So 1, negative 3 appears to be another solution. So let's test it out in the second one. We know it works in the first one because that's how we got the values. Put a 1 there. 1 squared is 1, negative 3 squared is 9, 9 and 1 is 10. That checks out. So it appears in my solution is the ordered pair 3, 1 and 1, negative 3. So we can write the solution as, or in a solution set as 1, negative 3 and 3, 1. Now notice if I had used these in the second equation, okay, put a 3. Notice here, if I put a 3, say in the second equation where the x is, this would be 3 squared is 9, subtracted from 10 is 1, y squared is equal to 1, so I get then y is equal to plus or minus 1. Okay, so this says, okay, 3, 1 and 3, negative 1 works. So we know that 3, 1 works because we tried that one already, but 3, negative 1, it's not going to work in that first equation because I put a 3 where the x is. I get 6 minus 5 is 1. Okay, so the 3 and the negative 1 are not going to work. The 3 and the 1 will. So when you plug an equation, the values in the second equation like this, and you're using the square roots, make sure you check all your solutions. So the only ones that are going to work, if I go ahead and plug in the 1, okay, when x is equal to 1, put a 1 where the x is. 1 squared is 1, subtracted from 10 is 9. So y squared is equal to 9, y is plus or minus 3. Well, the y negative 3 work because you put a 1 there in the first one and I get the negative 3, but I don't get the positive 3. Okay, so always make sure you check your solutions when you plug in. It has to satisfy both equations. In order to satisfy the system, it has to satisfy both. Okay, so the only solutions that I have for this one then are 1, negative 3 and 3, 1. Those are the ordered pairs. Okay, and the next one I have the system x squared plus y squared is equal to 1, which represents a circle, and the second one is y is equal to x squared minus 9, which is a parabola. So again, I could have no solution if the graphs do not intersect. I could have 1, I could have more depending on the intersections. So on this one way to do it is since the second one is out for y, I could replace the y by x squared minus 9, and it will work out. But it's a little bit more complicated because notice, because of the square, this is going to become x to the fourth minus 18x squared plus 81. So it's going to give me a 4th degree equation. Okay, so what I did here is I took the second equation and solved it for x squared. Bring this minus 9 over. So that would read x squared is equal to y plus 9. I rewrote it with the x squared on the left side, but it's the same thing. X squared is equal to y plus 9. Okay, so what I'm going to do then is I'm going to use this substitution right here into the first equation. So where I have an x squared in the first equation, I'm going to replace it by y plus 9. Okay, so y plus 9 right here where the x squared is, plus y squared is equal to 1. So then I just rewrote this y squared plus y. I brought the 1 over, subtracted it from the 9, so that's 8. And then this is a quadratic equation, y squared plus y plus 8 equal to 0. Normally you try to factor. This one doesn't factor. We did some others by factoring. This one doesn't factor here. So I used the quadratic formula. Okay, x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Okay, that's your quadratic. So in this case, the coefficient of the square term is 1, so a is equal to 1. The coefficient of the y, or the first degree term, is 1, so b, that's b, is equal to 1. Remember, the quadratic has the form ax squared plus bx plus c is equal to 0. In this case, the variable is y. So b is equal to 1, and the constant, that's c. c is equal to 8. So I just plug that into the equation. Okay, so x is equal to, and then on the numerator it's minus b. b is 1, so that's how I get this minus 1. Plus or minus the square root of b squared. b is 1, so b squared is 1, so that stays 1. Minus 4, the 4 is part of the formula. 4ac, a is 1 and c is 8, so I get this. And then in the denominator it's 2a. Okay, 2a, and a is 1, so that's how I get this 2 times 1. Okay, so I get that under the radical it's 1 minus 4 times 1 times 8, so that's minus 1 minus 32, which is a negative 31. Okay, now when we're dealing with solutions of systems of equations, we're looking for real solutions. Okay, because I have the square root and under the radical I have a negative, this is an imaginary solution. So there are no real solutions. There are no real solutions to this system of equations. So since we're looking for real solutions and we only have imaginary solutions, then there's no solution. So I use the notation for the empty set. No solution. Okay, this concludes this video. We have one more video for this particular chapter, and then we're going to go on to the next chapter in our course that we teach, college algebra. So again, if you have any questions or suggestions, please post them, and please subscribe, and we'll see you in the next video.